In this related rates example, we're being told that a spy is watching a rocket that took off from a launch pad 10 kilometers away from the position of the spy. Here's a quick visual example of this situation. We are also told that at a certain moment, the angle of elevation of the telescope that's watching the rocket is pi-thirds radians, and that it's changing at a half a radian a minute. Specifically for that information real fast, if we called this angle right here theta, that matches the horizontal, the ground, with the angle of the telescope, we're being told that that angle is pi over 3 radians and that that angle is changing at a specific speed. We're being asked to find the velocity of this rocket. Before we break down all the information given to us in this problem, I want to look at the picture that I've created here and make sure we understand the variables in play. We're trying to relate this angle right here of elevation to this rocket right here, specifically the velocity. The velocity of this rocket, since we're considering this rocket only to go completely vertical, is all about vertical height. To relate these variables together, what we could do is create this triangle right here that matches this angle and the rocket's height. All right, the next thing I want to do is look at what we want to know in this question. In this question, they're asking us is what is the velocity of the rocket? For me, this is why it's useful to create the picture first so I can create variables for this situation. I'm trying to figure out how fast this rocket is moving vertically. And in this case, I labeled this measurement right here to be h. Now, nothing in this problem is telling me what h is, though I know that if this h measures the height of the rocket, the change in the height over time would equal the velocity of the rocket. So in this context right here, what I would want to know is dh dt, or the height of the rocket over time. And with more detail real fast on the units, I would know that the height must be measured in kilometers. I know that because the only other distance I have is in kilometers, and the only other measurement I have as far as time go is in minutes. All right, now we want to figure out what we know. The first piece of information was said that at a specific time when the angle was pi-thirds radians. I labeled this angle of elevation right here as theta. So in that case, in the instance that we're looking at, theta would equal pi-thirds. We're also being told that that angle is changing at half a radian a minute. So if theta is my angle, then that rate would be d theta dt, or the change in the angle over time. And that was half a radian a minute. Now comes the step of wanting to relate the information that I have. Again, the measurements that I have right here are details about theta. I introduced the idea of height because this would help me deal with the height of the rocket. And I'm also told about this 10 kilometers right here. Specifically, I know nothing about this diagonal at any certain moment, though I can relate those three values right there using the tangent function, right? If I think of this as a right triangle right here, tangent of theta would be h over 10, or opposite over adjacent. Just to make the point too before I move forward, is that I am using this, though I could alternatively, because we now know the inverse trig functions, I could use this version of this statement to tackle this problem. And at this point, we know in order to tackle this related rates, once we gathered all our information, our job then is to differentiate with respect to time. By the way, time in this case is minutes. When I differentiate this left side with respect to time, the derivative of tangent, the outer function, is the secant squared of theta in this case. Then I need to also multiply that by, using the chain rule, d theta dt. On the right-hand side here, then I'm going to differentiate this. By the way, the 10 is simply a constant. I don't need to worry about that. In fact, I can write that 1/10 outside and then differentiate the h with respect to t. That gets me out this rate right here. All right, things are looking really good. Now what I have is an equation that relates theta and d theta dt and dh dt. And again, d theta dt is that the rate at which the angle is changing. Dh dt is the rate at which this height is changing, which we discussed earlier is equivalent to finding the velocity of the rocket. Now I'm simply going to plug in my values. I know theta is pi over 3, so this becomes the secant squared of pi over 3. d theta dt was 1/2 radian per minute, so I'll just put 0.5 right here. That equals 1/10 of dh dt. Before I calculate this, I'm just going to multiply 10 to both sides to get rid of this factor of 1/10. Then I simply calculate 5 times the secant squared of pi over 3. Quick note, if you don't have secant on your device that you're using to calculate this, you can use the actual unit circle to calculate this, or just do 1 over cosine squared, which is the way that I would tackle this. 5 times 1 over cosine squared gives me 20. Finally, I need to add my units to my information, and I had done that work in the beginning. That's always useful when I'm tackling this. The rate of dh dt, or the velocity, the change in the height of the rocket, is kilometers per minute. Make sure we know what reasoning for that was. It's kilometers because our other information in this problem were measured in kilometers. T is in minutes for time because that other rate right here was also measured in time. So this is kilometers per minute.